is Professor Melanie Matchett Wood, Rutgers, PhD from 2009. We're very happy to have him back. We'll speak about factoring random polynomials. Unfortunately, Philip cannot make it for dinner, so we cannot have dinner today, but hopefully another time.
All right, thank you very much. Glad to see you all here. I regret first typo on the slide here. It's not actually September 27th, for anyone's confused. November 8th, sorry about that. Okay, so I want to talk about whether polynomials are irreducible over the integers. So if you just pick a random polynomial somehow, you could think, can I factor it using only integers? And this question goes back a long time, and it's sometimes called Hilbert's irreducibility theorem. And it says you use a certain model. So you fix a constant degree d, and we look at a polynomial h of x. We'll assume the first coefficient is 1. That's often just for simplicity, so you're not factoring out 2 from all the terms in the polynomial. So it's x to the d, ad minus 1 times x to the d minus 1, all the way down to a0. This is monic polynomial, so the first coefficient is 1, degree d, and you choose these coefficients uniformly and independently from integers and minus k to k. And the theorem says this polynomial is irreducible with probability approaching 1. So here's an example polynomial. I set d equal to 2 and chose this with some kind of random measure, minus 4,376. Who thinks this is irreducible? Well, if you believe the theorem, the odds should be good, right? These are pretty big numbers. And if you think about this, what it would mean for this to be irreducible over the integers, you know from the quadratic formula if b squared minus 4ac, right? If b squared minus 4ac is not square, then it's irreducible. Then it's irreducible in ZB. And so that gives you a clue as to why this would be true. If you think about this class of polynomials has 2 degrees of freedom, but the class where they're factoring, where this is a square, has a degree of freedom less. And so that argument, Van de Verden essentially developed in 1934, showing that if you fix the degree, the space of factoring polynomials has 1 degree of freedom less. It's a space of polynomials that's a dimension lower, and so it has measure 0 in the whole set. So this is one kind of way in which the average polynomial is irreducible. Here's a different model that looks similar in some ways, but there's a big difference. Now, instead of letting the coefficients get bigger and bigger, we'll let the degree get bigger and bigger and keep the coefficients small. So in this case, the coefficients a, d minus 1, a1, and so on, they're going to be 1 or 0. And for this, because we're I guess we could think, let me back up a tiny bit. What do you think for Hilbert's irreducibility theorem? So Hilbert's, the probability that this polynomial, I guess let's call it h, is reducible, you can factor it, there's a natural lower bound. And that comes from the case when the constant coefficient is 0. Right? In this model here, a0 is 0 with probability 1 over 2k plus 1. So there's some zeros in the interval, it could hit 0. That would mean that the last coefficient is 0, you factor an x out. So this is a lower bound for the probability of irreducibility. And in this model, if we were allowing this to be 0 1/2 the time, we see a half. So we'll just say right away that we will disallow that from being a possibility, and now make coefficients in the that are not the lead coefficient or the constant coefficient, let them be independently 0, 1, probably 1/2. And this is much harder. So there is a conjecture, and there's exciting news on this conjecture that I will get to later in the talk. A conjecture from a while ago. How many of you here weren't yet born in 1993? Anyone? Okay, so far so good. Someday the answer will be yes to that, but I haven't had it happen yet. So the probability that G is irreducible goes to 1 as D goes to infinity. This is conjectured by Leedsko and Koonin, and it's hard. It's a hard result. It's not. Even the news you heard later is not proof in full of the conjecture. And this is the best result from a while ago, and is the best unconditional result even now. The probability that this polynomial is irreducible is at least some constant over log d, where c is a positive constant as d goes to infinity. So what happens to this bound as d goes to infinity? goes to 0. And so this is, whereas we were hoping the conjecture is that you get something going to 1. So even an unconditional result that this is at least 0.05 or 0.001 is not known.
But for any fixed d, you can find it empirically, numerically.
Yeah, so you could if you pick, you could just write this. There are only so many. There are 2 to the d minus 1.
Did anybody try to bother to tabulate for small d?
In fact, as you'll so one of the points of this great experimental question. So that idea also, I think, thanks to my exposure to Professor Zylberger back when I was a student, occurred to me, and a colleague of mine organized an REU of 4 undergraduates to investigate this experiment, to study, to see what does it look like when you just count these, and could you just check to see what, do you get, how close do you get to being reducible, how big should B have to be for this to work out? And so and that was motivated, there are these 2 models. There's the degree is fixed, the coefficient's growing. Degree is growing, coefficients are fixed. There's also intermediate things, both growing, both growing together. You could also ask questions, did it matter that we're choosing them independently? Or if you chose a different model where they weren't fully independent but were well-behaved in some way, would you get some kind of irreducibility behavior that way? And so I want to say a little bit more, give you another result.
But intuitively, or heuristically, most of them are irreducible.
Are irreducible.
Yeah.
Yeah, so it is.
So it's not surprising to them.
Yeah, I guess. Well, it is. I guess it's. I mean, I suppose they're mostly irreducible. It kind of depends how you're counting. At the fixed degree, you're counting up. Here, the dimension of your space is increasing each time you increase d. So you're looking at a family of the spaces that are increasing in dimension. And maybe it shouldn't be surprising. I mean, one thing that I find sort of interesting about this is if you looked at this in a finite field, the answer is completely opposite. Like in finite field, it's very rare to get irreducible. Most of the time you can factor. So that's a special thing about finite fields. And so maybe this is maybe it's clear it should be this way. But let me state a theorem that explores a little bit how this, at least in the Hilbert's case, how quickly it should approach 1, and how close you should be to this typical, you could think of this is maybe the typical way for it to factor. Maybe that's the primary way that it factors, and this theorem due to Chela essentially shows that. So this is from 1963, and I'll phrase it, Chela was doing a counting result, but I'm going to phrase it as a probability result because I like to call myself a probabilist. So we're thinking this is take the probability that you have one of these random polynomials h, and this is of the sort where the degree is fixed and the coefficients are growing. And the probability that h is reducible divided by the probability that h of 0 equals 0. That's maybe your typical, the simplest way for the polynomial to factor. This goes to some constant, c of d, as d goes to infinity, and this is explicit. It's explicit. It depends. There's a volume term, and there's also a Riemann zeta term. So that's a.
CD.
Oh, it's C. Yeah, it's an explicit constant that depends on d. And of course, in this case, in the Hilbert's reducibility theorem, d is one of the constants. And that's the sort of funny thing, that d is that, right, we're assuming d is a constant, so for each d, there's this constant, it depends, I think the dependence on d, part of the dependence is there's a volume you're looking at, d-dimensional volume you look at, yeah.
So what is the limit? D. Right now, that makes sense.
Oh, I have it wrong. Yes. That does not make any sense. Okay, good catch. So this is not, I'm going to say something later when t goes to infinity, but let's first say this is as k goes to infinity.
Okay.
Right, so in this model, good catch. Sorry, that's at least type of number 2, if not more. So k is going to infinity. So as k goes to infinity, you fix some d, then we get this constant d, c of b that depends on d. And it's explicit. Taylor has a formula for it. And the one thing I will say also, so first you take this limit as k went to infinity, but as you then look at this limiting constant, as d goes to infinity next, so first k went to infinity, now d goes to infinity, C of D goes to 1. And that says that indeed, as the degree increases, you do tend to get the typical, this h of 0 being 0, that is the main contribution. As the degree is bigger, it's not as the degree is small, it's not necessarily the case. So let me actually, I'll go to the next slide and show you a figure with some of the data these students have collected. So to emphasize again, factoring, something very simple, we just mean we can break the polynomial into two smaller polynomials where the degree is strictly lower than the original degree. And here, yeah, this is maybe part of what, that draws a bigger question. So these are the 4 undergraduates from University of Madison: Christian Borst, Evan Boyd, Claire Brekken, and Samantha Solberg, who worked for a summer doing some programming in Magma and using a distributed computing system so they could run the sampling across many computers. And they're looking at the kind of coefficients, polynomials from the Oblitsko-Punin conjecture, these G, we call G of X, where the degree is going to be growing, and the coefficients A, let's see, A1E plus 1. These coefficients here are all 0 or 1 with probability 1/2. So for the small cases, up to degree 21, the computer system was enough that they could compute the probability exactly and do a complete count of all the polynomials, divide by the total, and have an answer here. And what this dashed line is a lower bound. So one way, here's another audience participation moment. So x to the 7th plus x to the 5th plus x to the 4th. This is one of these polynomials g, plus x cubed plus x squared plus 1. This is not irreducible. This is reducible. It factors. Does anyone want to guess why? The simplest way would be if the constant coefficient were 0. That's not true. What would the next simplest way for it to factor be?
You can simplify then everything separately.
Yeah, I mean, one way that would be simple is maybe there's a linear factor. And the linear factors that you can have in this particular case,
X plus 1.
yeah, you can if you plug in -1, so this is f of, this is g of x, g of -1 here, right? This is negative, 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 3 negatives, 3 positives. This is 0. So we have a linear factor. That also, and so this dashed line, the dashed purple line here, I can't even see this. Well, the dashed purple line is the lower bound from this group. So dashed purple is from asymptotic number of polynomials with -1 as the root. Or meaning x plus 1 as you said. If x plus 1 is the factor of the polynomial. And that seems, and so this is an interesting commonality that here the simplest way of factoring was the dominant contribution. Here we can't have this linear factor where of x coming out because we chose the constant coefficient to be 1, but we can have a linear factor x plus 1 factoring out, and that seems to be the dominant contribution as x increases. So I did say this is exact counting all the blue dots. The green dots here are then sampled randomly, and they used, I think it will say, I think you'll see, they used enough sampling so that the sampling error is not visible on this graph. So even taking the level of, so people know this, if you're a physicist and you want to collect, you want to discover something, like the Higgs boson, that's a statistical statement. It means they got a whole lot of data, and it was so much data that the chance that they could have seen this data and there was no Higgs boson is less than 1 in a million, roughly speaking. It's a 5 standard deviation about that's discovery. Evidence is only 3 standard deviations.
So there's no rigorous proof with the Higgs.
Yeah, it's a statistical statement. And so the sampling done here, the students also use, the error bars are not visible, they're small enough. They have enough data that even with the 5 standard deviation physicist discovery level, you still have very small error. So these, I'm very confident all these samples are quite close to being what you see plotted there. So, yeah, let me talk a little bit then. There's one of the ideas we'll kind of see coming through more is that the simplest way of factoring was the dominant contribution. So the dashed purple is the linear factor. In the case of Taylor's result, it's explicitly comparing to this linear factor of x. And here is some data the students produced. Yeah, this is explained. Yeah, this is some of the standard deviation information I was mentioning here. I'll talk about that in a second. But let me talk first about Taylor's result. So it's exactly this probability of reducibility. So this is the chance we give a factor, and we're expecting that to go to 0. And that's divided by this other quantity we know goes to 0, the chance that we had 0 as a root. And what the students noticed, these blue dots here, so the red line is the constant CD. It's an explicit constant. They can plot that for various values of d. That is what the red line is showing. And even these blue dots, when k is equal to 3, the blue dots converge very rapidly to Taylor's limit. But Taylor's limit wasn't about k equals 3. It was k going to infinity. And so in a certain sense, the k being large didn't seem like it was so necessary. Even degree 8, k equals 3 are already incredibly close. And here the orange squares are approaching more quickly. Their k is 10. And the green triangles now k is larger, k is 100. Those start out closer to Taylor's limit all the time. But one of the things that the students liked about this is that it shows there's this limit as k goes to infinity that we know is approaching Taylor's limit. But it also seems to approach Taylor's limit very rapidly if you let the degree increase, and not even increase very much. Degree 10 doesn't seem like giving away too much to get the result there. So that, yeah, so this is one thing. So this confirms at least Kopunen's conjecture. It suggests the decay rate should be this 1 over, or 2 over, this is a little hard to read. It's 2 over pi times d all square rooted. That comes from just counting. The students could count the number of polynomials that have minus 1 as a root. And yeah, this is our 5 standard deviation confidence interval. It's 0.0025. You wouldn't see that on the graph on the left. The confidence intervals you'd see on the one on the right are a little bit bigger. And they did a lot of sampling still. This t is the number of samples here, so up to 4 million samples. The reason it's bigger here is that in Taylor's theorem, you're dividing by this quantity that gets smaller. And so when you set k equal to 100, you're dividing by 200. That made the confidence intervals bigger by a factor of roughly 200. And so that's why this last confidence interval, 0.25, you could actually see 0.25 as this. It would show up on here if they applied it in. But it's still a reasonable average. Maybe it's close. So this is the setup. I'll say one thing about this idea, the simplest factoring is the one that controls the probability. There's a reasonably recent result, I think just last year, that I will say that it takes a nice step towards at least Kopunen's conjecture, and that is this result of Barry Sorker and Kozma. And what they show is that if f of x is a polynomial like the one in Kopunen's conjecture, the coefficient we're going to call b now plus b0. And the reason is that b is uniform on not 0, 1, but 1 up to 210. Does anyone have a special relationship with 210? So it's not arbitrary in this particular case. That was the smallest they could make the number. It's divisible by 4 distinct primes, and the proof they use needs to have the range span interval divisible by 4 distinct primes. And so this is that is an impediment that would stop this method directly of proving at least Kopunen's. But in this case, they do show that the probability that f is irreducible does go to 1 as the degree increases. So this is the coefficients. They're fixed. They're not so small. They're 200 to start with these go to infinity. And so small cases of that, when the degree was 10 and k was 100, they're similar to what's going on here. But it's the same. It's the same sort of feature where they can prove irreducibility. And again, here it's expected that what is controlling what is controlling the probability of factoring is the simplest factor. That should be a linear factor. And there'll be another thing I'll go say about that next. So, what are questions or comments so far?
Yeah, why do we exclude the linear triple one?
Yeah, so that's, I mean, I will write, I think, next. There's a heuristic that we had in the paper. Let me write that out. Is this board too far away? Maybe I'll put it, I'll erase Chio's and put it here. But there's so part of the paper was developing a heuristic that essentially said that the factoring should be controlled by the smallest possible cases, and if you exclude those, by the next smallest possible cases. So actually, let me before I write the heuristic, let me show you some more data. This is, after all, the experimental math seminar, so let me go to the next slide and show you a slightly different case, but I think one that's interesting nonetheless. So now, instead of 0, 1 coefficients, we'll have plus minus 1 coefficients. This means the constant coefficients usually we can have to be a random variable as well. So, and I'm going to state a result of this is direct work with Sean O'Rourke that's about this kind of polynomial, although the method here is more general. If you have degree at least 1, and f of d is this polynomial, degree d, the coefficients are a d minus 1 down to a1, down to a0, I guess. And they're IID Rademacher random variables. So Rademacher was a statistician, and according to Wikipedia, he's the one for whom you should name plus minus 1 with equal probability random variables. So that's the kind we're using here. And then the result with Sean says there exists a sequence kd of natural numbers of infinity if you take the degree big enough, so that the roots of fd are algebraic of degree at least k with probability going to 1. Now that sounds, let me translate this algebraic, maybe you know this already, but in case you don't, algebraic degree k, so I guess what this says is you don't have roots with small algebraic degree. So no degree k algebraic roots means no factors over the integers over z of degree k. And so this doesn't prove irreducibility, but it says you can't have, that you're unlikely to have small degree factors. And it's interesting because the heuristics that we saw before were that the small degree factors mainly control the main probability. And so the factors that you actually expect to see, this result shows that they're low probability. Well, then there needs to be a different argument saying that you don't get any high degree factors. So here is, I want to go to the slide, there's some data. So the students, again, Borst, Boyd, Brekken, and Solberg, did a similar counting problem for these Rademacher plus minus 1 polynomials. And something immediately became apparent. But you see the blue curve and the green curve. They're different. And there's a good reason for that. The blue dots correspond to cases where the degree is odd. So if you think of a good odd degree case like 1, x plus 1, this can have minus 1 as a root. But this cannot have plus or minus 1 as a root because it's sum to an odd number of terms. So the even degree cases, as over f, they have this feature. You cannot, it turns out you can show that for these plus minus 1 polynomials, all the roots here are all they're all between 1/2 and 2. This is not, there's a geometric series argument you need to show this. So the roots, if you think geometrically, they're all in the complex plane and it's annulus, and the only integers are plus 1 and minus 1 that you could have. So the only linear factors you could have here are plus 1 and minus 1. You can't have those linear factors if the degree is even. And so the behavior is different, where the probability of factoring is much smaller, and the students only had, they didn't do statistical analysis, they only had anecdotal analysis, but when they saw things at factors, it seemed like it was because there was a quadratic factor. And you could, another next step, they might have shown this purple dashed line is a lower bound based on the presence of a linear factor, x minus 1 or x plus 1. I think you could also show a lower bound for four polynomials that could have a quadratic factor that would track these peaks here. So there are a few interesting things to point out about this. One of those is, so one of those things is that there are also these peaks that are lower still, right, that are not at this sort of quadratic level. I think those are cases where you can't have a quadratic vector either. There's some elementary condition that lets you say you cannot have a quadratic vector. But there's this interesting thing from Galois theory that there are some of these dots that are very close to 0 that are actually exactly 0. And it's a little surprising why that works, but I'll just say a tiny bit, since you've all maybe had to, or will have, or took recently a qual in algebra. The idea is that in a finite field with two elements, you can ask, is this polynomial irreducible? The all ones polynomial. Every coefficient here is a probability. Every coefficient here, this is not random. Every coefficient is 1, and it's degree d. And the answer is yes for a subset of degrees d. And it's related. I think we even have a small paragraph giving the outline of how you do this. In a number 3 course, this might be sort of an advanced exercise, but it's related to something called Argand's conjecture that you can always remember that 2 will play a special role. And so there's this thing. The Argand's conjecture says that this list of primes is expected to be positive density in all the primes, and roughly 38%. And so that suggests that this pattern should continue. You keep having these spots that are all very close to 0.
Is that sequence is famous?
Yeah, this is if you look on I guess I have not checked the online integer sequences database. I imagine it should be there, but this you can see it. Wikipedia, if you look at Argand's conjecture, will tell you. But we'll have this list starting there because those are the primes that satisfy. Yes. And so these are the primes. Well, it turns out I think they need to be. If you add 1 to each of them, then they're the primes. Right. If the primes, in our case, the primes are not good because those are the odd degree. Okay. So we actually need the things that are when you just take one away to get the primes. So right. Good catch. So at least it's a verbal mistake. These are not primes for anyone watching back home. Those are all even numbers. Okay, so so let me.
So they're called Argand primes. 1 to n 1.
That's possible. I'm not sure. I would have to check to be sure. But this Argand's conjecture in general is exactly what produces this list for primes that have this special feature. So one other thing, I mentioned this heuristic. So I wanted to write down in this. We had the students. They did this large computational project. Let me just say a little bit about how they. I mentioned a few words about how they did the project. Let me write. You see maybe a tiny bit of pseudocode. So what were these students doing, computer-wise? Math-wise, they were doing things like computing what this limit should be asymptotically. It's reasonably elementary combinatorics, but still it's something that they could do and prove. But let me say about what the heuristic was that we came up with in the final paper. Yes, here it is. So this heuristic, I'm calling it a heuristic because we did have a lot of evidence for it, but maybe not enough evidence to make a formal, actual conjecture about it. This is from Borst, Brekken, Wood, Solberg, and also both faculty sponsors, me and Melanie. No, Melanie's first, because she's alphabetically first. This is from 2017, and it's published in the Journal of Experimental Mathematics. Our heuristic is, and I'll phrase this vaguely because that's how we wanted to state it, if f is a well-behaved polynomial, and that includes the examples where the coefficients are independent